This is video 14 for artificial intelligence. In the last video I talked about the partial order planning algorithm and set out the way in which it operates and tries to construct a plan by essentially making modifications to a partially finished plan in order to try and turn it into a finished one. One of the key things about that algorithm is that there are choices to be made, particularly in terms of choosing a precondition to try and satisfy. And having chosen which precondition you want to satisfy, then choosing a way in which to satisfy it, which can either be by introducing a new step or by using a step that's already in your partial plan. And that begs the question of introducing heuristics into planning, because we've seen in earlier algorithms that do any kind of search with backtracking, and in this case we're searching for a complete plan that does what we need, that choosing the order in which we explore parts of the search space can have a significant effect on how long it takes to find a solution. Now, for partial order planning, it's a little bit more tricky than anything we've seen before, because in particular we don't have any real straightforward representation of a state, because our state now is a partially completed plan. And it's not obvious how we might measure any kind of sensible distance between a partially completed plan and a goal. Now, with a little thought, you can come up with possibilities that seem sensible, such as the number of currently unsatisfied preconditions, or perhaps the number of unsatisfied preconditions minus the number satisfied by the start state. The problem there, though, is that we now have actions that can have multiple effects, and that means that a single action can achieve more than one precondition. So that suggests that using these as heuristics might be overestimates. And another issue here is that because the effects of an action can clobber preconditions that are already achieved by other actions, these heuristics may give significant underestimates if actions are kind of highly interactive, if they can affect each other in multiple ways. So the question now of designing a decent heuristic for something like the partial order planning algorithm becomes a lot more interesting. Now, we could take inspiration from what we saw about making heuristics for CSPs and think in terms of something like the most constrained variable heuristic. And that would lead us, for example, to a preference for choosing the precondition that has the smallest possible number of ways of being satisfied. And here we're essentially going to be trying to force backtracking to happen sooner rather than later. Now, that in itself can be a tricky thing to compute. So we can look in terms of choosing preconditions that can't be satisfied, which clearly is a case of backtracking immediately if you can, or choosing preconditions that only have one way of satisfying them. But these are still kind of straightforward and basic, and it turns out that we can do much better than this. And we can do that using the idea of a planning graph. Now, these pretty much revolutionized the field of planning when they appeared. They give you a much nicer way of constructing good heuristics to use in searching for plans. And they also have the pleasant side effect that they can be used on their own to generate plans, if that's what you want to use them for. In either case, the process is pretty straightforward. So these are the kind of algorithm, well, I don't know about you guys, but I see algorithms like this and I think, wow, I wish I'd thought of that, because it really is elegant and clever and just the sort of thing that makes being a computer scientist interesting. Planning graphs apply when you can propositionalize your planning method. Now, all that means in our case is that if we look at the strips language that's being used by the partial order planning algorithm to represent actions and goals, preconditions, and so on, anything that involves variables can be expanded out into a set of propositional equivalents. And all that you have to do in order to achieve that is look at all the constants that appear in the problem and assign them to variables in all possible ways. So here on the left I have a specific action description that involves the variables x and y. And in the algorithm as I've described it so far, you would instantiate those variables by binding them to specific constants, like home or joke shop or hardware store and so on. In order to propositionalize that, we replace it by the collection of actions on the right. And these are precisely the strips version with the variables in, but with the variables substituted for constants in all the ways that we can think of. And now we have a propositionalized version of the planning problem. We just apply this method to everything that we can. Once you've propositionalized everything in this way, actually constructing a planning graph is fairly straightforward. And I'm going to move on to a specific pictorial example in a moment. But the basic idea is this. You start with a level of 0, which corresponds to your start state, namely a bunch of propositions that describe the start state for your problem. Then we build up the graph in a series of levels that correspond essentially to increasing time, and at each level we approximately keep track of all the things that could be true at the corresponding time. And we also keep an approximate track of what actions we might be able to take at the corresponding time. Now it's only approximation because we don't take all of the conflicts between actions into account. And that means that we will generally underestimate how long it might take for a particular proposition within the graph to appear. Now by that I mean that if you think in terms of what we've already said about partial order planning, a proposition such as at the hardware store may not become true until we've executed a number of actions. And the time at which it becomes true can depend on how earlier actions interact with one another, in the sense that some may clobber others. And here, because we're not going to keep track of all the possible conflicts between actions, we're going to generally end up underestimating how long it takes to make something true. And it's underestimates that we want for designing good heuristics. So let us see an actual example, once again involving the guerrilla purchasing roof climbers. Now in order to be able to actually draw this, because these graphs can become big and complicated, I need an even simpler example. So the roof climbers will have to inflate their inflatable gorilla before they can attach it to a distinguished roof. So here's an even simpler planning problem. Initially we have a start state which is empty, and I'm going to use the underlying assumption here that anything that's not specifically mentioned in the state is false. So the start state for this problem is in fact that we don't have a gorilla and the gorilla isn't inflated. And our actions, well, we have two again. One says that if we don't have a gorilla, we can buy a gorilla and then we will have a gorilla. And the second says that if we have a gorilla and we inflate a gorilla, then the gorilla is inflated. And the goal is to have a gorilla and for the gorilla to be inflated. You will of course not have too much trouble working out how to come up with a plan here, but this is just complex enough to allow the idea of a planning graph to be illustrated properly. Now the way in which this works is that we begin with level 0, in fact S0, because we divide levels into state levels and action levels. And level S0 here describes our start state, which is that we don't have the gorilla, and the gorilla is not inflated. Then we have the first action level, A0, and it contains all the actions that could be carried out at that point in a plan on the basis that their preconditions appear in the preceding state. So in this case, the initial state S0 only has not h of g and not I of g. If we look back at our actions, buy gorilla is possible because its precondition is not h of g. Inflate gorilla is not possible because its precondition is h of g. Now h of g doesn't appear in state S0. Now we also have these intriguing looking little guys. These are called persistence actions, and they let us keep track of what happens to an element of a state if we don't do anything. So the top one denotes the fact that if in one state it's the case that we have not h of g and we do nothing, then in the next state, level S1, we still have not h of g. Similarly for the lower of those two persistence actions, and the presence of by g in the action level A0 means that because by g has an effect, which is h of g, we have the gorilla, h of g then appears in state level S1. And this is how we build the graph. If we now move on from S1, we look at all the actions that are possible given the propositions that appear in state S1. And so there will be a persistence action for each proposition within S1, namely one for not h of g, one for h of g, and one for not I of g. And now in state level S1 we have preconditions for both of the possible actions, by g and inf g. So both of those actions appear in A1, and all of their effects, in addition to the effects of the persistence actions, appear in state level S2. So that's a fairly nice, straightforward way in which we can start with a problem description that's propositionalized and start constructing this graph. Now we need some further additions to this graph in order to keep track of some of the interactions between propositions and actions. Now what do I mean by that? Well, so there are 5 special kinds of edge for this graph. These are all called mutex links, but there are 5 different kinds of them. And the first one denotes the fact that the effects of 2 actions are inconsistent. So if the effect of one action negates the effect of another action, then those 2 actions are mutually exclusive. And in the current example, I have a persistence action here, which has the effect not h of g, and I have the by g action here, which has the effect h of g, and because h of g is the negation of not h of g, these 2 guys are mutually exclusive, hence the green edge here. The second kind of mutex link is for when actions interfere, which means that the effect of one action negates the precondition of another. So in this case, I have a persistence action whose precondition is not ig, and an action inf g whose effect is ig, which is the negation of not ig. So now the persistence action and inf g are mutually exclusive, and we mark that with a mutex. For the third kind, now we say that 2 actions are mutually exclusive if a precondition for one of them is mutually exclusive with the precondition for another. And I'll come on to what it means for propositions within state levels to be mutex in a moment. But in this case, we have a whole bunch of actions that are mutex because they're competing for preconditions. So just to take one of these as an example, by g has the precondition not h of g, and inf g has a precondition h of g, and these are already mutually exclusive, so by g and inf g are mutually exclusive as well. So we have a mutex here. And the argument for the other mutexes between actions in level A1 is precisely the same. The fourth kind of mutex, and now we're moving on to mutual exclusion between propositions in state levels, just denotes the fact that you can't have a proposition and its negation together at the same time. So any proposition is mutex with its negation. And the final kind says that all pairs of actions that could achieve a pair of propositions are mutex. So in this case, we find that the only pair of actions that can achieve not hg and ig in this state level are the two actions infg and this persistence action, and they are mutually exclusive by this mutex here, and that's the only pair of actions that can achieve not hg and ig at the same time, and they're mutually exclusive, so not hg and ig are mutually exclusive as well. And if I go through and apply this to the current example, then these are the mutexes that I get. So I filled in all of them here, up to and including state level S2. Now the construction of the graph in this way continues until you get two levels that are the same. At that point you can stop. And after you get to there, well, what can you say? Well, the first thing is that any proposition that doesn't appear in the final state level is something that you can never reach. But more usefully, by looking at where things appear for the first time, you can get an estimate of how costly it is to make that proposition true. So the level cost of a proposition is just the level that it first appears at. Now, that may not be an accurate estimate of how costly it is to achieve that proposition, because it may be that several actions can be carried out simultaneously at each level, and the level cost doesn't count the number of actions that are needed. Now, one way around this is to make a serial planning graph which includes mutexes between all pairs of actions except the persistence actions, and then use level cost in a serial planning graph. Now that's fine for estimating the cost if you want to achieve a single proposition, but of course our planning problems involve goals which can involve achieving a whole bunch of propositions. So now we have various things that we can potentially come up with in terms of estimates of how costly it might be to achieve a collection of propositions. Max level is exactly what it says it is. You use the maximum level in the graph of any proposition in the set that you're trying to achieve. The level sum uses the sum of the levels of the propositions that you're trying to achieve. And the set level uses the level at which all the propositions appear, with none of them being mutually exclusive. And the accuracy of these is going to depend somewhat on the problem. And in particular, a little thought should convince you that the level sum heuristic here may be quite accurate if the goals can be decomposed, in the sense that you can try to achieve each one individually and independently of the others. Whereas the set level heuristic may be accurate if the goals aren't decomposable. As a general statement, if you have a planning graph, then if a proposition appears at some level, there may be a way of achieving it at that point. But if a proposition doesn't appear at some level, then it can't be achieved at that point. And this is a direct consequence of the fact that we're only looking at interactions between pairs of items namely the ones that are linked by mutex links. And we now have precisely the kind of trade-off that we've seen in some of the earlier algorithms in this course, which is that if you track more interesting interactions and you go beyond mutex links, then you're going to get a closer approximation to the reality of the planning problem than if you just use mutex links. But as usual, the trade-off then is increased computation in order to keep track of these interactions that are now more complex than just looking at pairs. And once again, it seems as though the sweet spot here is just to look at mutexes on the basis that you often get decent heuristics from the graph just using mutexes, and using anything more complex ends up being something that you pay for by having to spend more time in actually working with them. Now that allows us to use a planning graph along with things like level sum, set level, and so on, in order to get heuristics that we can then extract and apply within the context of other planning algorithms. But we can go a little step further and get the GraphPlan algorithm, which allows us to use a planning graph with a couple of extra steps and turn it into a planning algorithm in its own right. And that's quite a straightforward thing to do now we have the concept of a planning graph. We start at level 0, and as usual we have a loop that we keep going around until either we've found a solution or established that there isn't one. And the idea is simple. If all the goal propositions appear in the current level of the graph, and no pair of them has a mutex link, then we're going to attempt to extract a plan. And I'll talk in a moment about how we go about that. If that's successful, we're done. If we can tell by analysing the graph that there is no solution, then we're done. Otherwise, we just expand the graph to the next possible level. Now, termination can be proved for this, but I'm not going to go into that because that's pretty tricky and would take too long. The only question remaining then is how we go about trying to extract a plan once we've got to a level where all the goal propositions have turned up and none of them are mutex. So, how does this work? Well, in the running example, we've got as far as a situation that looks like this. Now, if we look at state level S0, clearly we don't have the two goal propositions that we need. In S1, we still don't, but in S2, we have both have gorilla and inflated gorilla, and they're not mutex. So, at this point, we can try to extract a plan from this graph. Now, this is kind of fun, because extracting a plan from the graph can be treated as a search problem. And the reason for that is that we have a fairly straightforward and clear-cut way in which to express extraction of a plan in terms of states and actions. And we can do that as follows. We now set up an intelligent search problem where states correspond to levels within the planning graph, and each possible state has a collection of the currently unsatisfied goal propositions. Now, the start state is just the final state level for the graph that we're trying to extract a plan from, along with the relevant goal propositions. So, we've got to this point, and we start off with a search problem having a start state that corresponds to S2 with the two circled predicates, because they form the goal. Now, actions within this search problem can be defined as follows. Let's say I have a state which corresponds to a level and which contains some unsatisfied propositions. An action within my search problem is to select a bunch of actions within the preceding level in the planning graph in such a way that no pair has a mutex link, no pair of their preconditions has a mutex link, and the effects of the actions that I've chosen achieve the propositions in my current state. And finally, the new state that this gets you to within your search problem for doing the plan extraction has a level corresponding to the preceding state level in the graph, and it contains the preconditions for the actions we've selected. Now, this takes a little bit of unpicking because unfortunately now I have to talk about two different kinds of action. Actions within the planning graph and actions within this intelligent search problem for extracting a plan. But hopefully, if I continue the pictorial example, this process will become clear. So here is the running example, and this is the situation we've found ourselves in. At this point we can try and extract a plan because S2 contains both of the propositions that are required by the goal of the planning problem. Okay. Now this slide is divided. At the top we have the planning problem in the form of the planning graph, and at the bottom we have the intelligent search problem that's extracting a plan from the planning graph. So, concentrating on the bottom part of this diagram for a moment, what you can see here is the operation of an intelligent search problem going from one state to the next by applying actions. So this is the start state. On that start state, we do an action like this, which is made up of actions taken from within the planning graph. That gets us to this state, and then this action gets us to this state. Okay? But you need to keep in mind that these are two separate problems. It's just unfortunate that for both of them I have to talk about states and actions. So you need to keep those separate in your head. So now the start state for the intelligent search problem is this guy here. The start state corresponds to a state level within the planning graph, namely S2, and some propositions that are unsatisfied that we aim to satisfy. Okay? Initially, HG and IG, because they form the goal. And the idea here is straightforward. We work backwards towards the beginning of the planning graph. And the aim is, at each step, we're doing a search to find a combination of actions within the planning graph that will achieve the propositions we need at the next level of the planning graph. At that point, the aim becomes to achieve the preconditions of those actions. Okay? So in the intelligent search problem, our first step, which is this one, our first action within the intelligent search problem, corresponds to a collection of actions within the planning problem that will achieve our currently unsatisfied propositions, namely HG and IG, and which are not mutually exclusive, and for which the preconditions aren't mutually exclusive. And our next state within the intelligent search problem is then this guy, which corresponds to the preceding state level in the planning graph, and also contains a new collection of propositions that we need to achieve. In this case, because the actions we're picking out are inf_g and a persistence action, inf_g here, and a persistence action here. Now these are chosen because they achieve IG and HG, and they're not mutually exclusive, and their preconditions aren't mutually exclusive. In fact, they share a single same precondition HG, and their preconditions, in this case just HG, form the content of this new state in the intelligent search problem. So we've started at the end of the planning graph. That corresponds to a start state for the intelligent search problem, and then the intelligent search problem has performed an action moving back one level to this new state here. And it's done that by saying, I want to achieve HG and IG. I can do that using infg and a persistence action, and the preconditions required for that are just HG. Okay, and we can continue in this way. And this is possibly a little tricky to unpick, but I'm hoping that you can see how this corresponds to an intelligent search problem that we can use to try and extract a plan from the planning graph. Now, in this case, it's particularly simple, and we're quite constrained in terms of how we can move forward. At this stage, there is only one applicable action that we can apply in the start state. We can't make an action that includes ByG in order to achieve HG, because the only thing we would be able to pair it with to achieve IG would be infg, and there's a mutex link between ByG and infg. In a real and more interesting problem, from this start state, there may be multiple ways of choosing some actions at level A1 that don't have mutexes, that don't have mutex preconditions, and that achieve the propositions in the start state. And so we have a search graph or a search tree instead of the case here, which is very constrained and linear. Now in this case, we can finish off the process. Now we've got to this state in our search problem. It has HG. Now we want to move to a state corresponding to S0. That means we have to find an action in our search problem denoted by some actions within our planning problem. We want actions that achieve HG. There is only one choice, that's ByG. It has HG as an effect. It's a single action, so it can't be mutex with any of the other actions needed to achieve HG. And it only has a single precondition, not HG. And because that's a singleton, it can't be mutex with anything. So we can just take this ByG action out here to make an action within the search problem. And now we're happy, because our intelligent search problem has got to a goal here. And the reason for that is that it's got to a point that corresponds to the initial state level in the planning graph, and the only propositions involved are ones that are already achieved at state level 0, namely not HG. Okay, so perhaps it might look a bit clearer if I actually wrote not H of G in here. So in general, GraphPlan will work by constructing the planning graph, waiting until all the required goal propositions appear, and then running an intelligent search algorithm to try and extract a plan. And in this case, we can see that that works, and that our plan is that first we ByG, and then we inflate G, and we're done. And if that fails, In the more general case, then GraphPlan will extend the planning graph out by another level and have another try. Now, as a final point here, having just introduced an intelligent search problem, we can of course apply heuristics to that part of the process as well. And once again, we need to look at what's going on and try and propose sensible heuristics for this case. And these are just a couple of suggestions as to how we might get started with that. But I'm not going to labour that point and go on and talk further about heuristics for this particular intelligent search problem, because now I want to move on and talk about how you can alternatively address planning problems by re-encoding them either as SAT or CSP problems.